Okay, so let's simplify this. Let's think about what this actually means. X squared is x times x, and x to the third is x times x times x. So hey, I've got 5 x's all multiplied together, x to the fifth. So in other words, when you have the same base and you're multiplying, you can just add the exponents together, because that would equal x to the fifth, right? This next one, let's think about what this means. We've got x times x, and that's multiplied by itself 3 times. So I've got 6 x's all multiplied together. This is x to the sixth. So when you've got an exponent raised to another exponent, you're going to multiply the exponents together, okay? So if you forget that these people mix these up a lot, if you forget, just make yourself a simple little test like this, because if you know what x squared means and x raising to the third power means, you can figure it out if you need to, okay? All right, let's simplify this. So you can actually distribute, sort of. You can think of that as distributing. So this is going to wind up as x squared, y squared. Because if we think about what this one means, we've got xy times xy. Okay, and then x times x is x squared, y times y is y squared. So it works out like that. Okay, so you can do the same kind of thing over here, and if you actually multiplied this binomial by itself, remember there would be 2 3's, 2 x squareds, and 2 y to the thirds, right? So when you distribute the exponent, don't forget to distribute it to the 3 as well. People forget to do that sometimes. Okay, so I'm going to be squaring each of these parts. So I've got 3 squared, which is 9, x squared squared. So maybe I should write this out here. Got that, right? And then I've got this. So then that's going to simplify to 9x to the fourth, y to the sixth. Okay? All right, so here is the big mistake. So since you can distribute in over one term like that to the different variables and coefficients, people assume that you can do this. But you can't. That's wrong. This is wrong. Because you got to think of this, when you've got more than one term in there, you got to multiply it out. Think of that as, we're going to FOIL this, right? It's a binomial times itself. So, first would be x squared. Outer would be xy. Inner would be yx, which is also xy. And last would be y times y squared. And then I can combine those pieces in the middle. So I'm going to get x squared plus 2xy plus y squared. Okay? And then we talked about this before, but when you have a negative exponent, you can write that with a positive exponent like so. Okay, it's going to be 1 over, and then the exponent turns positive. Okay? So, very simple mistake that gets made on this next problem. A lot of people will say, oh, okay, so then this is going to be 1 over 2x to the third. But this is wrong. You can't do that either, because the 2 isn't raised to the negative 3. If I had the quantity 2x raised to the negative third, if I had parentheses around the 2x, that would be a different case. But really this is 2 to the first times x to the negative third. So I can rewrite this part as 1 over x to the third, but the 2 wouldn't go down with it, okay? And then so, I could think of that as 2 over 1 times 1 over x to the third. So this is going to look like that when I'm done. So the 2 doesn't move down with the x to the third because it's not raised to a negative exponent, okay? Oh, and here's the example I was just talking about over there. This is different because now this whole quantity is raised to the negative third. So this would be 1 over the quantity 2x to the third, okay? And now we can actually simplify that further. It's 2x times 2x times 2x. So the 2 is going to get cubed, and so will the x. So I've got 2 to the third is 8. X to the third is x to the third. So 1 over 8x to the third. Okay? All right. Anything raised to the 0th power equals 1. Okay? If you've got a fraction like this, then then what you can do, well, here, let's think this through for a second. Got 5 x's there. I've got 3 x's on bottom. So we can cancel some of these, right? Those will cancel, these will cancel, those will cancel. And then I've got 2 x's left in the numerator, so this is going to equal x squared. So little shortcut, hey, what's the relationship between 5 and 3? Well, I mean, to get a 2, you could subtract, right? The thing you need to be careful with is you're subtracting the top exponent minus the bottom one. It doesn't, you're not just going to do the bigger number minus the smaller, because sometimes you'll end up with something like this. So if we think through this, then, you know, the 3 x's on the top will cancel with those 3, and I've got 2 x's down there, but this doesn't just equal x squared. I got to remember they're in the denominator, so I'd still have 1 up top. So this is going to be 1 over x squared, also known as x to the negative second, right? So yeah, you can use, I would usually use the subtraction thing, especially if you've got some bigger numbers, but I was just trying to show you why this is the case, okay? So that's going to lead me to x to the negative second, which would simplify to that, right? Okay. So getting back to why something, anything to the 0th power equals 1, if you think about this, well, what if we had x to the 3rd over x to the 3rd? Well, if you subtracted, anything over itself equals 1, right? And then, hey, that equals x to the 0th, right? So you can use this subtraction rule of exponents to describe why anything to the 0th power would equal 1, okay? All right, so, all right, next problem. I'm going to start simplifying this, and here's how I like to think of these. I kind of split these into different parts, and you know, I don't always draw in these parentheses, but this is kind of how I think of this. I think, okay, 2/4 is going to reduce to 1/2. Okay, and then with the x's, I can subtract the x's, so x to the 3rd, and then x to the 1st, so that would, if you did the canceling, you'd wind up with 2 x's in the numerator, right? And for the y's, you'd end up with 2 y's in the numerator if you did the subtraction. So you don't really need the 1 up there. It's not a big deal if you leave it there, but you could simplify that to x squared y squared over 2. Okay. Okay, on to the next page. All right, now I've got x over y, the quantity x over y raised to the 3rd power. So again, think of this as x over y times x over y times x over y. And if you multiply straight across, that's what you get, right? So you can just cube both the numerator and the denominator, okay? Next up, when I've got something, a fraction raised to a negative exponent, it would equal 1 over x over y to the 3rd power, but there's a nice shortcut that you can use. Just take the reciprocal of the fraction, because 1 divided by x over y is going to turn out to be y over x, and then you've got that raised to the 3rd power. So just flip the fraction, and then that will turn your exponent positive, and then we could simplify that like so. We could distribute the 3, right? Okay, so let's do the same kind of thing. And we got some different options. You could start distributing the -2 to all the pieces in here, to the 2, the x, the y, the 3rd, and so forth, and do the same thing in the numerator. But when I have got a whole big fraction raised to a negative exponent, my first step is just flip the whole thing upside down, take the reciprocal, and then I've got a +2 out there, and then I won't have to deal with as many negative exponents, okay? So we got some different options here. Again, you could start squaring everything, or you could start simplifying the fraction. I think I'm going to simplify the fraction, might as well, because then there'll be less to square. So I'm looking at the 6/2, and that would give me 3, right? 3 over 1. So I'm going to put a 3 in the numerator there. And then the x's are goners. Those will just cancel out. And for the y's, I'm going to have y squared in my numerator, and there's nothing in the denominator. So I had already written the fraction bar, but I didn't really need it. So I've got the quantity 3y squared squared, okay? And then it's 3y squared times itself. But I'm going to just distribute here. So 3 squared is 9. Y squared squared is y to the 4th. So 9y to the 4th. Okay. All right. So let's move on. Remember, when I have the same base, you can add the exponents together. So yeah, it's true. You could simplify the 5 to the 1/2. So it'd be the square root of 5, and then this would be the square root of 5 to the 3rd, and you could start working out like that. But when you have the same base, you might as well combine the two pieces here. So then we've got this is going to be 5 to the 4/2. Now wait a second, 4/2 is just 2, so I've got 5 squared, 25. Not bad. Okay. All right, and hey, I've got the same bases here, and I can subtract, right? I can do the top exponent minus the bottom one, and that will combine those two pieces. Okay, so then I've got 4 to the 4/2. That's 4 to the 2nd, and that is 16. Okay. All right, and this one's kind of a mess. So here I can see I've got x's on top and bottom, y's and z's, right? And then some of them are raised to negative exponents and some are not. So what I like to do on problems like this is just pull down the pieces that are negative exponents, that have negative exponents. So I'm going to pull that down, okay? And I'm going to pull this down as well. The y to the negative 3rd, since it's already downstairs, I'm going to pull that upstairs. So any piece that has a negative exponent, I'm going to use the stairs, and then it will have a positive exponent on the other floor. Okay, so the 2 is going to stay where it is. So my x's are moving downstairs, so I'm not going to have x's down there. I have a y to the 1st already living upstairs, right? And then now there's going to be a y to the 3rd as well. Okay, so these are all going to be multiplied together. Okay, and then my z's are moving downstairs, so I'm not going to have any more z's. All right. For x's, there's already an x to the 1st down there. Now there's also going to be an x to the 2nd. Okay, and there was already a z down here, and now a z to the 3rd is moving down there as well. Okay, and now I can just simplify everything. So now looking at the numerator, I've got 2y to the 4th, right? I'm going to have 3, and then there will be 3 x's, x to the 3rd, and 4 z's, z to the 4th. And there we go. Okay. Okay, next page, we're going to look at some radicals. Okay, so here is a property that hopefully you're familiar with already. So if you have two different radicals, two different square roots, you can combine them if they're multiplied together, you can combine them into one, put them under the same root. You can do the same thing with cube roots. If they're both cube roots, you can do the same thing. So you can always do that when you're multiplying if the index is the same in both radicals. Okay, so looking at this example here, hey, I've got the same index. Let's put this all under the same roof. And then that's going to be 8, right? But I'm going to be looking for triplets, so I might as well keep breaking up the 4. And hey, I found some triplets, so this is going to simplify to just 2. Okay? All right. Next up, I've got a radical in the denominator here. And so we've dealt with this before, but we've only seen it with square roots. So we want to rationalize the denominator, which means we're going to write this so it doesn't have a radical in the denominator anymore. Okay? So what a lot of people are tempted to do is this, because this is kind of what we did when we had square roots. Okay? But the problem with that, if I do this, then I'm still not going to have triplets in that. I'm not going to have triplets down here in the cube root. So I want triplets, so I only had one x. I wanted 2 more x's, so that's actually what I want to do. so that I can release the x's out of the prison there. Okay, so on top, I got that. Okay, on bottom, now I'm in business here because I got my triplets. So got it down to that, okay? And I'd still want to look to see if there's anything else I can do, reducing fractions, or I don't have any triplets there, so I'm kind of done. But a lot of times you'll still be able to do some more simplifying after you rationalize the denominator, okay? All right, so here are some more properties, which hopefully you're familiar with this as well. When you have the square root of a fraction, you can split it into top and bottom, or you can combine it if it's useful. You can do the same thing with a cube root or a fourth root or a fifth root, and it's going to work like that, right? So looking at this one, I have no idea what the cube root of that whole fraction is, but let's break this apart. A lot of times that will help. Okay, now I could start rationalizing the denominator, and nothing wrong with that, but I'm looking at the top and thinking I got some triplets there. Okay, so I'm thinking of money. I'm thinking $1.25 is 5 quarters, right? 5 times 5 times 5. So let's I'm gonna simplify the numerator first. Got some triplets there. That's the 125, and then I could write out all 6 x's if I wanted to. Or you could write x squared times x squared times x squared. I mean, you don't really have to write these out, but you kind of want to be thinking about that. How many triplets do you have with those? And so, got triplets there, triplets here, triplets there. So the top is going to become 5, and then 2 x's will get out, so 5x squared over the cube root of 6. Okay. Now this is going to make it a lot easier to deal with when I rationalize the denominator, okay? So I don't have any triplets, it's just 2 times 3, so let's get some triplets like that, okay? Or you could just call that 6 squared, or even 36, right? So maybe I'll just write that as 36 up there. X running out of space there. Okay, so let's see what we got now. On top, I've got 5x squared cube root of 36. And on bottom, I'm going to have 3 6's all underneath the cube root. That's going to simplify to just 6. Okay. And I'd still want to look to see if I have any triplets here. So I'm thinking, oh, that's 6 times 6, so 2 times 3 times 2 times 3. But there still wouldn't be any triplets. Also, I can't reduce the 5 6, so that one is good to go. Okay, doesn't really look too much simpler from the original, but it's considered simpler because we don't have a radical in the denominator. Okay. All right. Next up, these are like terms, so you can add them together. Hey, I got 2 of these plus 3 of these. These being root x's, so that means you're going to have 5 of those. Okay. All right, now this one, it's tempting to say, oh, I've got 5 of those again, but you don't because the index is different, so that means these are not like terms. So you can't simplify. They're not like terms. Okay, you need like terms for addition or subtraction. Okay. Okay, on to the next page. So these were like terms. They have the same index and the same radicand. Here we have the same index, but not the same radicand, right? So this is apples and oranges again. These are not like terms, and so you can't simplify this one either. Okay. Now, looking at the next example, I would totally understand if someone looked at this and thought, well, those aren't like terms, I can't simplify it, so it's done. But you want to be careful because this part's in simple radical form, but the root 50 is not. So let's put it in simple radical form and see if we do have like terms after that. Okay, so let's see. I've got 3 root 2, and then root 50. I can think of that as 5 times 10, right? So that's 5 times 2, and hey, that's going to simplify to 5 root 2. So I've really got 3 root 2 plus 5 root 2. So it was disguised, but I actually do have like terms, right, when you put them in, both in simple radical form. So this is going to simplify to 8 root 2. Okay? Same kind of thing is going to happen on this problem because I can still simplify this piece. Okay, so 27 is 9 times 3, or 3 times 3 times 3. Okay, and so I've got 5 root 3 minus 3 root 3. 5 of those minus 3 of those, I'll end up with 2 of those. 2 root 3. Okay. Okay. All right. Next up, it's tempting on this next problem to think of 3 times 4 to the 2/3 as 12 to the 2/3. See that all the time, but that's incorrect. You can't do that because it's really 3 to the 1st times 4 to the 2/3, right? Same thing here. This is not equivalent. This piece is not equivalent to 28 to the 2/3 because you'd have to do the exponent first, and it's 7 to the 1st and 4 to the 2/3. So you can't do that. Okay, so don't do that. All right. So what can we do? Well, I do have the same, these things, we could write these as radicals, right? They would have the same index, and they'd have the same radicand as well. So, hey, I do have 3 of those plus 7 of those. That means I'm going to have 10 of those. Those being 4 to the 2/3. Okay? So I've got it down to that. And again, this does not equal 40 to the 2/3 because it's 10 to the 1st. Okay? But let's try simplifying this piece by writing it as a radical. So if you're stuck on these, try converting anything with a rational exponent to a radical. Or if you have a radical, try converting it to an exponent. And then a lot of times it'll get you somewhere. So I've got the cube root, right? That's going to be my index. And then I've got 4. And I could square afterwards, but I can't really do the cube root of 4. I can't do anything with that. So I'm going to try squaring it first. So let's see, maybe I've got some triplets down here. And I do actually because, oops, got the cube root there. Because I got 4 times 4, well that's 2 times 2 times 2 times 2. I do have some triplets here, right? So I've already got the 10 out there. Now a 2 is going to get out. And then I get that last 2 stuck there forever. So this is we're going to end up with 20 times the cube root of 2. So all of these problems I'm writing in simple radical form. That's generally what we want to do, unless we're asked to round to the nearest hundredth or something like that. Then you use a decimal. Okay. All right. Next up. Now these do not have the same base, so you can't just write this as 27 to the 6th or something like that. It's not going to work like that. But what we can do is to write them with the same base, because 3 to the 2nd is 9, right? So I can take 3 to the 4th, and then I can write this as 3 to the 2nd to the 2nd, like that, right? So this is actually going to be 3 to the 4th times 3 to the 4th. Okay, so if I wrote out all those 3's, I'd have 8 3's all multiplied together. So this is going to be 3 to the 8th. And then I still would need a calculator for that. But, I mean, I guess I could sit there and multiply it out. But this is going to come out to 6,561. Okay. All right. All right. And we've already done problems like this, but a little reminder to rationalize the denominator. We're going to do this. Okay, and then I still need to reduce, and you can't reduce the one that's inside the radical, but you can reduce these two, so this simplifies to just the square root of 3. Okay, all right, next up, I've got radicals in the denominators again, but this time it's not as simple as just root 5 down there or root 3. I've got another term. I've got these binomials, okay? So if you try to do this, which I see a lot of people do, it's actually not going to get us anywhere, okay? Because on top we'll have 2 root 5, and that's fine. But on bottom, you'd have to distribute the root 5. So you'd have 3 root 5, And then root 5 times root 5 would be root 25, which is 5. And so you still got a denominator in the, a radical in the denominator. So this is a dead end. Okay, that's not going to do you any good. So we're going to do something else. What we are going to do instead is multiply by the conjugate of the denominator. So if you remember back when we were looking at roots, at conjugate roots, the conjugate of this, you change the sign of the radical part. So the conjugate of 3 plus root 5 would be 3 minus root 5. Okay? And when you do that, I promise you if you do it correctly every time, you will not have a radical in the denominator anymore. Okay? So on top, I'm going to distribute the 2 to work down here. So this would be 6 minus 2 root 5 is my numerator. On bottom, I'm going to have to FOIL this, right? I'm thinking FOIL. So first would be 9, 3 times 3. Outer would be 3 root 5. Inner would be negative 3 root 5. Okay, and then last, and I find this is the part that people have the most trouble with, I've got negative root 5 times positive root 5. Oh, I don't know why I put that parentheses there, sorry. And last, I've got negative root 5 times positive root 5. Well, negative times a positive is negative, and root 5 times root 5 is root 25, which would be negative 5, okay? Root 5 times root 5 is 5. But I've got negative root 5 times positive root 5. Okay? A lot of people get the sign wrong there on that last part. Then I still have radicals, but wait a second. Those are just opposites. So when you multiply conjugates, you really only need to do the first and the last because the outer and inner are always going to be opposites. So then I've got 6 minus 2 root 5 over 9 minus 5. 9 minus 5 is 4. Okay? Now I still want to reduce this. And because I can see all 3 of these terms are even, okay? So you can reduce it all at once, and so, you know, they're all even, so I divide them all by 2. Sometimes people have trouble seeing that, so you could also split this, if it's helpful, into 2 different fractions, and then just reduce the 2 fractions. So I'd get 3 halves minus root 5 over 2. And then they have the same denominator. So, I mean, you could leave them like that. It doesn't matter. But you could also combine these into 3 minus root 5 over 2. Okay? So the mistake that I see people make sometimes is they'll reduce the 6/4, but then they'll leave the 2 root 5 alone. So you got to think there's 3 terms. So you have to have the same thing go into all 3 terms. Like you could factor out a 2 on top and then reduce the 2/4. And that would put you right here. Okay? All right, let's try another. So I've got, I'm going to multiply by the conjugate of the denominator, and that should take care of that radical in the denominator. Okay, and then I have to do the same thing to the top. So, let's see. I'm going to distribute up here. Got 8 plus 2 root 3. On bottom, I'm FOILing. So, first, 4 times 4 is 16. I'm not going to bother with outer and inner because I'm going to get 4 root 3 and negative 4 root 3. They'll cancel out. But last, I've got negative root 3 times positive root 3. Well, negative times a positive is negative. Root 3 times root 3 is 3 because it's root 9. Okay? And then I can simplify the denominator a bit. Okay, this time 8, 2 root 3, and 13. Nothing goes into all 3 of those. I can't simplify that radical anymore. And so I'm done. Okay? And that is the end. And I will see you next time.